This video is a reading of Chapter 5 of Paul Hewitt's Conceptual Physics. I'm going to read the introduction and sections 1 through 3. Chapter 5, Newton's second law of motion, force and acceleration. Kick a football and it moves. Its path through the air is not a straight line. It curves downward due to gravity. Catch the ball and it stops. Most of the motion we see undergoes change. Most things start up, slow down, or curve as they move. The previous chapter covered objects at rest or moving at constant velocity. There was no net force. The net force was zero, acting on the objects. This chapter covers the more common case in which there is a change in motion, that is, accelerated motion. Recall from chapter 2 that acceleration describes how quickly motion changes. Specifically, it is the change in velocity per certain time interval. In shorthand notation, acceleration is equal to the amount of change in velocity divided by the time interval. This is the definition of acceleration. This chapter focuses on the cause of acceleration, force, or I might add net force. The opening picture here, we got a loop-de-loop roller coaster. The thrill of a roller coaster ride comes from the acceleration experienced, not really the velocity, more the acceleration. Figure 5.1, kick a football and it neither remains at rest nor moves in a straight line. That means there must be forces acting on it. Section 5.1, force causes acceleration. Consider an object at rest, such as a hockey puck on ice. Apply a force and it starts to move. Since the puck was not moving before, it has accelerated. It has changed its motion. When the hockey stick is no longer pushing it, the puck moves at constant velocity. Apply another force by striking the puck again, and again the motion changes. The puck accelerates. Force causes acceleration. Most often, the force we apply is not the only force acting on an object. Other forces may act as well. Recall from the previous chapter that the combination of forces acting on an object is called the net force. Acceleration depends on the net force. To increase the acceleration of an object, you must increase the net force acting on it. This makes good sense. Double the force on an object and its acceleration also doubles. If you triple the force, its acceleration triples, and so on. We say an object's acceleration is directly proportional to the net force acting on it. We write it like this. Acceleration, that symbol right there, means proportional to net force. The symbol tilde stands for is directly proportional to. Section 5.2, mass resists acceleration. Push on an empty shopping cart, then push equally hard on a heavily loaded shopping cart. The loaded shopping cart will accelerate much less than the empty shopping cart. This shows that acceleration depends on the mass being pushed. The same force applies to twice as much mass results in only half the acceleration. For 3 times the mass, 1/3 the acceleration results. In other words, for a given force, the acceleration produced is inversely proportional to the mass. We write that acceleration is proportional to 1 divided by the mass. And if you think about it like this, if the mass gets bigger when you do 1 divided by the mass, you're dividing by a bigger number, it results in less acceleration, smaller acceleration. That's the idea of inversely proportional. By inversely, we mean that the two values change in opposite directions. Mathematically, we see that as the denominator increases, the whole quantity, 1 divided by the bigger quantity, decreases. The quantity 1/100th is less than the quantity 1/10, for example. Section 5.3, Newton's second law. Newton was the first to realize that the acceleration produced when we move something depends not only on how hard we push or pull, but also on the object's mass. He came up with one of the most important rules of nature ever proposed, his second law of motion. Newton's second law states the following. The acceleration produced by a net force on an object is directly proportional to the magnitude of the net force is in the same direction as the net force and is inversely proportional to the mass of the object. Or in equation form, acceleration is proportional to net force divided by mass. By using consistent units such as newtons for force, kilograms for mass, and meters per second squared for acceleration, we can get an exact equation. Okay, this equation right here, this is Newton's second law. Circle it, highlight it, put stars on it. Newton's second law says that acceleration is equal to the net force in newtons divided by the mass measured in kilograms. In the briefest form, where a is acceleration, f is the net force, and m is the mass, we can write a equals f over m. These are two different ways of writing Newton's second law. Words, symbols. Let's go check out this car racing picture. Figure 5.4. The great acceleration of the racing car is due to its ability to produce large net force. Okay, the acceleration is equal to the net force divided by the mass. From this relationship we see that doubling the net force acting on an object doubles its acceleration. Suppose instead that the mass of the object is doubled, then the acceleration will be halved, cut in half, because we're dividing by twice as much. If both the net force and the mass are doubled, the acceleration will be unchanged. Ooh, what does that mean? That means we're pushing twice as hard, but we have twice as much mass. Those things balance out and the acceleration stays the same. I'm going to skip this picture. Alright, let's read through this problem-solving example. If we know the mass of an object in kilograms and its acceleration in meters per second squared, then the force will be expressed in newtons. 1 newton is the force needed to give a mass of 1 kilogram and acceleration of 1 meter per second squared. We can arrange Newton's second law to read like this. Force equals mass times acceleration. Okay, so if we want 1 newton of force, that means 1 kilogram of mass multiplied by 1 meter per second of acceleration. 1 times 1 is 1. It takes 1 newton of force to accelerate 1 kilogram of mass by 1 meter per second squared. So we can see that 1 newton is equal to 1 kilogram times 1 meter per second squared. The dot between kilograms and meters per second squared means that the units are multiplied together. If we know 2 of the quantities in Newton's second law, we can calculate the third. For example, how much force or thrust must a 30,000 kilogram jet plane develop to achieve an acceleration of 1.5 meters per second squared? So we can calculate. We want to know how much force. Newton's second law tells us that the amount of force is equal to the amount of mass times the amount of acceleration. We have 30,000 kilograms of mass. We want 1.5 meters per second squared of acceleration. Multiply those, and it tells us that we need 45,000 newtons of force. Net force, actually. Suppose we know the force and the mass, and we want to find the amount of acceleration. For example, what acceleration is produced by a force of 2,000 newtons applied to a 1,000 kilogram car? So using Newton's second law, we find that the acceleration is equal to the amount of net force divided by the amount of mass. We have 2,000 newtons of net force. We divide it by 1,000 kilograms of mass. 2,000 divided by 1,000 tells us that the acceleration is going to be 2 meters per second squared. That's how much acceleration will result from this much force acting on this much kilograms of mass. What if the force is 4,000 newtons? Oh, that's twice as much force. What's the acceleration? Well, now we got 4,000 newtons acting on the same 1,000 kilograms. 4,000 divided by 1,000 equals 4. 4,000 divided by 1,000 is 4. So we get 4 meters per second squared of acceleration. Hey, look at that. Twice as much force, and we ended up getting twice as much acceleration. Doubling the force on the same mass simply doubles the acceleration. Physics problems are often more complicated than these. We don't focus on solving complicated problems in this book. Instead, we emphasize equations as guides to thinking about the relationships of basic physics concepts. The plug-and-chug problems at the ends of many chapters familiarize you with equations, and the think and solve problems go a step or two further for more challenge. Solving problems is an important skill in physics, but first learn the concepts, then problem solving will be more meaningful. Here's a couple check questions. Number 1. If a car can accelerate at 2 meters per second squared, what acceleration can it attain if it is towing another car of equal mass? Let's see. Okay, it can accelerate at 2 meters per second squared. If it's towing another car of equal mass, now we have two cars, we have twice as much mass, but the one car can provide the same amount of force. Twice as much mass means that the acceleration will be half as much. It'll be divided by 2. So the answer is going to be 1 meter per second squared. Number 2, what kind of motion does a constant force produce on an object of fixed mass? Okay, let's see. What kind of motion does a constant force produce on an object of fixed mass? Okay, so if it's a constant force, it's going to cause constant acceleration. So it's going to cause the object to speed up steadily. Speed up, speed up, speed up, speed up. It'll keep speeding up at a constant rate as long as the force stays constant. And by the way, right here when it says constant force, it means constant net force. The amount of net force is constant. It'll cause a constant acceleration. Goodbye.